Welcome to Kanerika's podcast, The Digital Shift. Imagine a mid-sized retail company on the morning of their biggest sales event of the year. For the past decade, their overnight batch reports ran perfectly.
Right, the daily sales numbers would just process quietly while everyone slept.
Exactly. And the executive dashboards were fully populated by the time the first cup of morning coffee was poured. But today, well, their business model has evolved. They're handling millions of real-time digital transactions, global inventory pings, and dynamic pricing updates every single hour.
Which is an incredible amount of pressure on a legacy system.
It is. Suddenly, the peak traffic hits. Their database query times triple, the operational dashboards freeze, the reporting is delayed, and the entire engineering team is pulled off development just to scramble and patch a system that is actively buckling under the pressure.
Meanwhile, their direct competitor, who modernized their data infrastructure a year prior, absorbs that exact same surge in demand and scales effortlessly without missing a single beat.
And that scenario is exactly why we are here today.
Yeah, that is the modern reality for enterprise organizations right now. And the crucial detail there is the timeline of the failure. Enterprise systems rarely fail instantly out of nowhere.
Right, it is never just a sudden snap.
Exactly. They fail gradually, they degrade imperceptibly over months as data volume increases, and then, well, they say all at once, the exact moment a critical concurrency threshold is crossed. Choosing the right foundational data architecture is your primary defense against that failure.
It essentially dictates whether a company experiences catastrophic operational bottlenecks or seamless, invisible growth. Which brings us to the core mission of today's analysis. We are dissecting what is arguably the most monumental infrastructure decision enterprise data teams face today.
The choice between Snowflake and Amazon Redshift.
Yes, and our objective is to move past the superficial benchmark tests that simply declare one platform faster in a controlled vacuum. We need to evaluate which architecture actually aligns with your specific operational workloads, your financial models, and your internal engineering capacities.
Because the gap between deploying the right platform and the wrong one is profound. I mean, it is not measured in compute milliseconds. It is measured in hidden engineering overhead, compromised operational agility, and whether your business can actually activate the massive volumes of data it collects.
So to evaluate how these platforms perform under sustained enterprise pressure, we really have to look directly at their architectural foundation.
Right, because physical architecture dictates absolutely every subsequent feature, limitation, and cost factor we are going to discuss.
Okay, let's unpack this architectural divide because their fundamental design philosophies could not be more different. If we need a formal visualization to ground this, think of Snowflake as leasing a vast fleet of highly specialized independent processing engines.
I like that analogy.
Thanks. These engines all pull from one massive centralized warehouse of cargo. You can dispatch a small engine for a light reporting task, or spin up a massive industrial engine for a heavy machine learning workload. And they operate completely independent of one another.
Right, completely isolated.
Traditional Redshift, conversely, is like owning a state-of-the-art, high-speed freight train. It is incredibly powerful, engineered for moving massive, predictable loads. But its engine and its cargo cars are permanently coupled together.
So you cannot simply swap out the engine without stopping and affecting the entire train.
Exactly.
What's fascinating here is how that separation or lack thereof manifests immediately in your daily operations. Snowflake was engineered from its inception for the cloud, utilizing a three-layer architecture that entirely severs storage from compute.
Meaning the data and the processing power are kept completely apart.
Yes, your physical data resides in cloud storage, but the processing power runs through independent virtual warehouses. This structural decoupling means that multiple departments can query the exact same data at the exact same time.
Wow, without any lag.
Exactly. The finance team can run complex end-of-month reconciliations, marketing can pull real-time campaign analytics, and data science can train predictive models all simultaneously.
Because they each use an isolated compute engine.
Right. There is zero resource contention. No one slows down anyone else.
Wait, hold on. If Snowflake completely separates the storage layer from the compute engines, aren't you introducing a massive network bottleneck?
How so?
Well, if the data isn't sitting on the same physical server as the processor, how does this not take forever just to send those massive data sets back and forth across the network?
That is the exact engineering challenge Snowflake had to solve. And they do it through aggressive micro-partitioning and local caching.
Caching at the compute level.
Exactly. When data is loaded into Snowflake, it is automatically broken down into highly compressed micro-partitions. When a virtual warehouse queries that data, it caches the results locally on the compute node.
Oh, I see. So if the marketing team runs a similar query 5 minutes later.
The compute engine doesn't go all the way back to the central storage layer. It just pulls directly from that local high-speed cache.
So the system gets smarter and faster the more concurrent queries it handles.
Precisely. And because of that complete separation of data and compute, Snowflake can execute some highly unusual metadata operations like time travel and zero-copy cloning.
But again, how does a feature like zero-copy cloning actually work without doubling your cloud storage bill? It sounds a bit like magic to just instantly duplicate a petabyte-scale database for a development team.
It is brilliant metadata management, honestly. When you execute a clone in Snowflake, the system does not physically copy the data.
It doesn't.
No, it simply generates a new set of metadata pointers that reference the exact same original data blocks. So you have two isolated environments pointing to one physical data set.
That makes so much sense.
Right. You only incur additional storage costs if the development team actually modifies their clone or adds net new data to it. Otherwise, that massive duplicate environment costs you nothing in storage.
That is an incredibly efficient use of cloud economics. Let us shift to the other architecture, though. How does Redshift's freight train approach compare when we look under the hood?
Well, Amazon Redshift was built on a massively parallel processing, or MPP, cluster model. In a traditional MPP design, storage and compute are strictly coupled on the exact same hardware nodes.
So the leader node distributes the query, and the compute nodes process the data they physically hold.
Exactly. Now, AWS recognized the limitations of strict coupling and introduced newer RA3 node types. These nodes partially decouple the architecture via Redshift managed storage,
allowing data to offload to Amazon S3, which is essentially AWS's infinite digital hard drive.
Right. However, the foundational architecture remains a cluster-based model. Isolating heavy workloads across different organizational teams still requires significantly more manual configuration, queue management, and workload management rules compared to Snowflake's default isolation.
So we have this decoupled architecture in Snowflake that isolates workloads seamlessly and a highly structured cluster model in Redshift.
Yes.
But how does that structural difference translate when our hypothetical retail company's peak season actually hits? Elasticity and scaling are where these theories are actually tested.
The contrast in elasticity is arguably the most significant operational difference. Because Snowflake's compute is completely untethered from storage, elasticity is near instantaneous.
Meaning you can spin a massive virtual warehouse up in seconds.
Yes. Run a heavy 2-hour data transformation job and then immediately suspend the compute.
And Redshift.
Redshift requires a fundamentally different approach. Going back to your freight train analogy, if you suddenly need to process twice as much cargo, you cannot just attach a new engine while the train is moving at 100 miles an hour.
Right, you have to slow down, pull into the station, and attach new cars.
Exactly. Resizing a Redshift cluster to handle sustained growth can take anywhere from 15 to 60 minutes. And crucially, it often requires a brief period of downtime or read-only access while the data redistributes across the new nodes.
Which means your engineering team has to accurately forecast demand well in advance rather than just reacting to it in real time. But that brings up a really important point about performance metrics. We constantly see these vendor debates focused entirely on raw speed. One platform edges out the other in a benchmark test by a fraction of a second.
Yes, the classic benchmark wars.
Right. I have to challenge the idea that raw speed in a vacuum is the most important metric for an enterprise data strategy.
I agree completely. Speed tests rarely reflect operational reality. If we look at ad hoc exploratory queries, the situations where business analysts are asking completely new, unpredictable questions, Snowflake generally performs faster due to its architecture.
But Redshift has its strengths there too, right?
Absolutely. Redshift is incredibly fast and largely unmatched for predictable, highly repetitive queries. This is especially true when Redshift leverages AccuUA, which is their advanced hardware-accelerated cache.
That essentially pushes the compute operations down to the storage layer itself.
Yes.
But there is a caveat to that blistering Redshift speed, isn't there? I've seen that it requires a significant amount of manual intervention to maintain.
Yes, and this is where engineering capacity becomes a deciding factor. Redshift is somewhat like a high-performance Formula One car. It will absolutely win the race, but only if you have a dedicated engineering pit crew constantly tuning the engine.
So it's not a set-it-and-forget-it system.
Not at all. Redshift requires a map to find data quickly. Data engineers must manually configure distribution keys and sort keys, which tell the system exactly which physical server holds which specific piece of data.
And what happens when you delete or update data?
Well, when you delete or update data in Redshift, it leaves empty gaps on the disk. So engineers must regularly run maintenance commands like VACUM.
Which is essentially a defragmentation tool.
Exactly. It sweeps through and packs the data tightly together so the engine does not waste time scanning empty space. And then that has to be followed by an analyze command to update the query optimizer.
Wow, so elasticity and raw speed only matter if the system can actually parse the data you are feeding it efficiently. And modern enterprise data pipelines are no longer just neat rows and columns.
No, they're chaotic.
We are dealing with continuous API streams, web application event logs, and highly nested JSON files. How do these architectures handle unstructured or semi-structured data?
This is a major differentiator. Snowflake was explicitly designed to handle semi-structured data formats like JSON, Parquet, and Avro natively. It treats them as first-class data types.
So if you have a deeply nested JSON object from a web application,
Snowflake automatically infers the schema. You can use standard SQL to query a value 5 layers deep just as easily as querying a traditional relational table.
that is incredibly convenient. What about Redshift?
Redshift historically treats JSON as a plain text string. To extract a specific data point, your engineers must utilize cumbersome string parsing functions or regular expressions.
It transforms a simple query into a complex, labor-intensive engineering task.
Exactly. While AWS has improved this with newer native JSON functions, querying heavily nested structures in Redshift is still fundamentally more rigid and resource-intensive than Snowflake's native approach.
All of this architectural design, scalability, and engineering logic ultimately hits the balance sheet. And the financial models governing these platforms are just as divergent as their architectures.
We definitely need to evaluate the actual cost of ownership.
Here's where it gets really interesting, because they operate on entirely different billing philosophies.
They do. Snowflake utilizes a consumption-based model, billing per second of active compute time. When your virtual warehouse is running a query, you pay.
And the moment it finishes and automatically suspends, your compute cost drops to zero.
Yes. This is highly efficient for organizations with unpredictable, highly variable workloads. However, at a massive enterprise scale, if queries are poorly optimized or warehouses are left running unnecessarily, that consumption model can lead to severe cost creep.
You pay precisely for what you consume, but the burden of monitoring that consumption falls heavily on your internal operations. What is the financial reality of Redshift's model?
Redshift leans into a traditional provisioned model. While they do offer a serverless option now, the primary financial advantage for enterprise teams lies in reserved instances.
Which means committing upfront.
Right. AWS offers 30 to 70% discounts in exchange for 1 to 3 year long-term commitments. If an organization has steady, high-volume, predictable workloads, Redshift is almost always the clear financial winner over a multi-year timeline.
But the monthly invoice from the cloud provider is only one dimension of the total cost. We must factor in security infrastructure and ecosystem integration, particularly for heavily regulated sectors like healthcare, finance, or government contracting, where compliance is non-negotiable.
Security introduces a critical nuance to the budgeting process. Both platforms are fundamentally secure, offering advanced encryption and comprehensive compliance certifications.
But the way they package these features differs.
Significantly. Redshift deploys within your virtual private cloud, or VPC, by default meaning it sits behind your private network wall. Furthermore, it integrates natively with AWS IAM.
Which is essentially the cloud's sophisticated bouncer, verifying identities and managing permissions.
Exactly. And Redshift includes advanced features like column-level security and dynamic data masking natively.
So, if a hospital needs to mask patient social security numbers from standard analysts while allowing executives to see them, Redshift includes that granular control out of the box.
Exactly. Snowflake, conversely, gates those advanced security controls like column-level security and dynamic data masking behind their higher-priced enterprise tiers, specifically the business-critical tier.
So if your organization requires that level of granular access control, you must factor the premium tier pricing into your Snowflake budget from day one.
You have to.
Beyond security, there is the broader strategic question of ecosystem lock-in. Redshift is strictly an AWS-first platform. It communicates natively and seamlessly with Amazon S3, AWS Glue for integration, and SageMaker for machine learning.
If a company's entire digital footprint is already built on AWS, choosing Redshift eliminates an enormous amount of friction.
Right. But Snowflake champions a strict multi-cloud strategy. It runs agnostically across AWS, Microsoft Azure, and Google Cloud Platform. If an enterprise is actively trying to avoid vendor lock-in, or if they acquire a company running on a different cloud provider, Snowflake offers architectural neutrality.
And deciding between native integration and multi-cloud neutrality is a massive undertaking.
This is exactly where we at Kanerika step in to bridge the gap between theory and execution. Because navigating this decision, analyzing concurrent workload patterns, forecasting multi-year consumption costs, and evaluating multi-cloud risk is incredibly complex.
It's not something you want to guess on.
Exactly. We do not just guess which platform suits a business. We conduct deep mapping of actual data pipelines. But more importantly, once an enterprise makes the decision to modernize, the actual migration is where the vast majority of projects fail or stall.
The migration phase is notoriously fraught with risk. You are not simply copying and pasting data from an old server to a new cloud environment.
That is precisely why we engineered Flip, our AI-powered data ops platform.
But as someone who understands the engineering complexity involved, when I hear that a migration is being automated by AI, my immediate reaction is skepticism.
That's completely fair.
How does an AI platform actually automate up to 75% of a migration safely without breaking deeply embedded dependencies or losing historical data integrity?
It is a fair point of skepticism. What Flip does is fundamentally different from a simple data transfer. It autonomously analyzes the legacy architecture. It reads the historical schema logic, identifies the dependencies within complex ETL pipelines, and then systematically translates the legacy SQL syntax into the optimized syntax required for either Snowflake or Redshift.
So it is mapping the relationships between the data, not just moving the files.
Exactly. By automating the syntax translation and schema conversion, Flip compresses what traditionally requires a large engineering team, months of grueling, error-prone manual effort into mere weeks. It fundamentally de-risks the modernization initiative.
That is a massive operational advantage.
We have mapped the physical architectures, we have evaluated the financial models, and we have established how to execute the transition using Flip. But we need to anchor all of this technical theory in tangible, measurable business outcomes.
Right. What does this unified data strategy actually deliver to the balance sheet?
Exactly.
I will share a precise scenario of a client we recently modernized. They were a globally distributed organization suffocating under highly fragmented regional systems. Each geographic region maintained its own isolated data silo,
Which makes reporting a nightmare.
Consequently, consolidating global financial and operational reporting required massive manual extraction and reconciliation. Executive reports were perpetually outdated, highly error-prone, and required multi-day cycles just to compile.
So what was the outcome after unifying?
Well, by utilizing Flip to unify their disparate infrastructure onto a single Snowflake architecture, they achieved a 60% reduction in manual reconciliation effort. They transitioned from frustrating multi-day reporting cycles to real-time cross-functional data access.
That is incredible.
For the first time, global supply chain teams, regional finance directors, and executive leadership were looking at a single, consistent, real-time view of their operations.
That is the exact definition of operational agility. And the scale of impact we drive at Kanerika extends deeply across specialized sectors. For example, in complex logistics and supply chain operations where real-time routing, fuel optimization, and inventory forecasting are critical to margins, we have delivered an average of $1.2 million in annual cost savings for our clients.
Because when the foundational architecture allows an AI model to instantly query global freight data without timing out, they can optimize routes with mathematical precision.
Exactly. The velocity of product innovation also shifts dramatically once the infrastructure bottleneck is removed.
Absolutely.
For our enterprise clients in fintech and health tech, we are seeing a 50% faster time to market for net new digital products. When a company's highest paid data engineers are no longer spending 80% of their week writing VC commands or manually parsing JSON strings, they can actually build revenue-generating features.
That makes perfect sense.
In the retail space, leveraging modern data platforms to execute smarter, highly dynamic inventory allocation and personalized pricing algorithms has led to a 28% boost in customer retention.
Wow, 28%.
And for pharmaceutical firms, where the sheer complexity of clinical trial data is immense, modernizing the foundation has driven a 30% reduction in project timelines, accelerating research visibility and overall operational efficiency.
Those metrics prove that the selection of a data warehouse is absolutely not an IT procurement decision. It is a foundational business strategy that dictates your ceiling for scale.
So what does this all mean? If we distill the architectural, financial, and operational realities we have explored today.
Snowflake generally wins when an organization requires strict multi-cloud flexibility, handles highly variable or unpredictable query workloads, and relies heavily on semi-structured data streams like JSON without wanting a massive engineering lift to parse them.
It allows concurrent departments to operate simultaneously with zero friction.
Yes. Redshift, conversely, wins decisively when an enterprise is deeply committed to native AWS integration, requires highly predictable multi-year costs for steady workloads, and demands default network isolation with native advanced security features like column-level masking included natively.
Without requiring enterprise-tier upgrades. Ultimately, migrating an enterprise data warehouse is a high-stakes engineering project, and we at Kanerika are positioned to architect and accelerate that exact modernization journey.
With your proprietary platform, Flip.
Yes, with Flip and our deep operational expertise in AI, data analytics, and intelligent automation, we ensure that an organization's infrastructure is not just updated, but structurally optimized for the future of their industry.
And this evaluation raises an essential forward-looking consideration for any leader mapping their technology roadmap today.
What's that?
We are rapidly entering an era where organizations are no longer just enabling human analysts. They are aggressively deploying autonomous AI agents to handle highly complex workflows.
Yes. Consider Kanerika's own suite of enterprise AI agents. Alan, who autonomously ingests, processes, and summarizes massive volumes of lengthy legal documentation.
Or Mike, the quantitative reasoning agent who continuously proofreads and catches deep arithmetic errors inside complex financial models.
And Susan, who autonomously scans, identifies, and redacts sensitive PII data across global networks to ensure strict compliance.
Exactly. As these autonomous AI agents are scaled across an enterprise, they will not simply be reading static, precompiled reports. To execute their reasoning, these agents will autonomously launch thousands of highly complex, heavily concurrent queries directly against your data warehouse every single minute.
That is a staggering amount of invisible compute load.
Right. When that inevitable scale is reached, will the elasticity, concurrency limits, and foundational architecture of your chosen platform support that synthetic intelligence? Or will your data warehouse become the ultimate bottleneck that brings your multi-million-dollar enterprise AI strategy to a grinding halt?
It brings us right back to the retail peak season scenario we started with. But this time, the massive spike in traffic isn't coming from millions of external holiday shoppers.
It is coming from inside the house.
Exactly. It is generated by your own autonomous AI workforce, testing the absolute physical limits of your data foundation, waiting to see if your architecture will fail gradually or all at once.